Hello, Physics 20s. In today's lesson, we are going to conclude the dynamics unit of study, and we're going to do that by 1. Applying Newton's third law of motion to explain, qualitatively, the interaction between two objects, recognizing that the two forces, equal in magnitude and opposite in direction, do not act on the same object. And 2, we've done this one many times. We're going to apply Newton's laws of motion to solve algebraically linear motion problems in horizontal and vertical planes near the surface of the Earth, ignoring air resistance. Newton's third law of motion. I suspect you've probably heard some kind of reference to it before. The wording might have been, for every force, there's an equal and opposite force. And yeah, that's what Newton's third law of motion is, but I'll give a bit more of a technical definition. So what I've said is if one object exerts a force on a second object, the second object will exert a force on the first object that is equal in magnitude and opposite in direction. Let's give an example of this. Let's say we have object 1. And object 1 is moving towards the right with some kind of unknown velocity. And then we have object 2 that is just sitting at rest. So these two are going to collide. Now, when these two collide, if I drew a partial free body diagram of object 2, when they collide, object 1 would exert a force on object 2. So if I'm object 2, I would feel the force from object 1 on object 2. So that's not F12, it just means the force 1 exerts on 2, and it'd be a force that's towards the right. What Newton's third law of motion tells me is that when object 1 exerts a force on object 2, well, if I draw object 1 then, object 2 would then exert an equal and opposite force back on 1. So we'll call that F21. F21 would just mean the force that 2 exerts back on 1. For example, if F12 was a force of 10 newtons towards the right, we'd write that down as positive 10. And then the force that 2 exerts back on 1, it would just be equal and opposite in magnitude. So that would then be negative 10 newtons. If you write down a mathematical equation to represent this, we would have F12 is equal to negative F21. And we can very, very quickly confirm that. F21 is positive 10 newtons. That would be equal to negative. F21 is in the opposite direction, so negative 10 newtons. Both sides of the equation, you'd have positive 10 is equal to positive 10. So this is the reason that if I decided to run up and do a flying drop kick at a wall, it would hurt. When I do the flying drop kick, I would exert a force on the wall, but in return, the wall would exert a force back on me. So that is not advisable. A few notes about this. 1, the force that gets things going, we call it the action force. So in the example I gave up here, the action force would be the force that 1 exerts on 2. Because object 1 exerts a force on 2, well, object 2 reacts to that. So object 2 exerts a force back on object 1, and we call that the reaction force. 2, we identified this in the first lesson of the unit, that forces always come in pairs because forces are always due to the interaction between two objects. And I can see the forces that, the pair of forces that I have here in the example identified. 3, each force of the pair acts on a different object. Okay, so there's a bit of a misconception where someone might say, so let me grab a different color. So for every force, there's an equal and opposite force, and you try to calculate the sum of the forces. Wouldn't the sum of the forces, for example, just be positive 10 newtons plus negative 10 newtons, which is equal to 0, which means my object would not accelerate. So the misconception would be, well, if for every force is an equal and opposite force, wouldn't those two forces just cancel each other off, resulting in a net force that is 0? Well, when I calculate the net force here, the net force I'm looking at is on just a single object. So for example, the net force on object 2 would just be positive 10 newtons. The net force on object 1 would be negative 10 newtons. These two forces, positive 10 newtons and negative 10 newtons, they don't act on the same object. They act on different objects. So therefore, you can't just take the two forces and add them up, because, for example, for object 2, the only force acting on it is the positive 10 Newton force. This negative 10 Newton force is not acting on object 2, so it doesn't cancel that force off. These forces act on different objects, and since they act on different objects, you would have a net force, and that would allow the objects to accelerate. One more example of Newton's third law of motion, we could look at a crate that's on the ground. So if you had a crate that was on the ground, well, that crate would exert a normal force on the ground. So we would call this the action force. I realize that you're probably thinking the normal force acting on the ground is the force of gravity. But you have to think from the perspective of the ground also is not allowed to pass through the solid box. So yeah, you would also, you could just classify this as a normal force. So the normal force would be the box preventing the ground from sinking through it. And then in return, because that box exerts a normal force on the ground would exert an equal and opposite normal force back on the box. So that would be the reaction force. All right, let's get into a pretty long example problem. So we're back to having a system. And in this system, we have an applied force FA1 that is exerted on mass 1 towards the right. So this 100 Newton force is FA1. And it causes the system to accelerate towards the right. I'm told the coefficient of friction between both boxes, and I want to A, figure out an equation for the system acceleration, the magnitude of it in terms of FA1, mu k, m1, m2, and g. B, we're going to plug some numbers in and calculate the system acceleration, and in the tension connecting masses 1 to 2. And then C, using our acceleration equation, we're going to identify which forces actually make up the net force on the system. All right, so this is just a normal dynamics problem, and we use the exact same procedure we've been using for all of the unit, which is we start off by drawing a three-body diagram. So let's do that for mass 1. Okay, so FBD of mass 1, what we'd have acting on this, well, we'd have the weight or the force of gravity straight down. Because we have two masses, I need to be specific about the subscripts. I'll say FG1. You have a normal force. that is equal in magnitude, opposite in direction. We're going to call that Fn1. You would have this force pulling towards the right, which we would call Fa1. You would have some friction that's opposing the direction of motion, so we can call that, I'll say Ff1. And we have another force too. If you envision yourself as the box M1 and you're being pulled towards the right, you would also feel the tug of this rope pulling you back because there's mass 2 that's being dragged behind. On a free body diagram, we're supposed to show all the forces coming from the center, but we can't really do that here because then we'd have two forces that point towards the left and overlapping. So I'm just going to draw the second applied force a little bit offset downwards. We'll just draw it so it points towards the left, but it just points a little bit further down off the center. And we're going to call that one Fa2. Before I get into the free body, let's do a mass acceleration diagram first. So MAD, M1, and the direction of acceleration is going to be towards the right. Before I get into the FBD of M2, let's write down all of our equations of motion. So let's start in the vertical direction. So assume up is positive. I'm going to find the sum of the forces in the vertical direction. There's no acceleration in the vertical direction, so that means the sum of the forces in the vertical direction is 0, which tells me that the forces in the vertical direction are balanced. Okay, expand the equation of motion. Fn1 points up, it's positive. Oops. Let's just quickly erase that. Okay, Fn1 is positive. Points up. Fg1 points down, it's negative. So you'd have Fn1 minus Fg1 equals 0. So expand this a little bit. This would turn into Fn1 minus m1 times g is equal to 0. And then this would tell me that normal force 1, if I add m1g to both sides, would just be m1 times g. I'm just going to box this one for now and call it equation number 1. To the horizontal direction, let's say right is positive, and I want to find the sum of the forces in the x direction. This time I'm accelerating, so that would be equal to mass times acceleration in the x direction. If you have acceleration in the x direction, that's a result of your forces being unbalanced. Okay, in the x direction, we've got a bunch of forces. So we have Fa1, it points towards the right, so Fa1 is going to be positive. We have Fa2 points towards the left, so it's negative. We have Ff1 points towards the left, also negative. And this would be equal to mass 1 times the acceleration is towards the right, therefore it's positive. Fa1 minus Fa2 minus Ff1 equals m1 times a. Okay, let's expand this a little bit. So let's turn this into Fa1 minus Fa2 minus, we're dealing with kinetic friction because the object's in motion. So kinetic friction is always just the coefficient of kinetic friction times the normal force. So this would be mu k times Fn1. And that's equal to m1 times a. I'm going to go one step further and make a substitution. So I'll just show this with a different ink color. I'm going to take this equation for Fn1 and I'm going to plug it in for Fn1 in the equation of motion on the bottom. Okay, so let's do this. I just want to get back to my purple pen color. Okay, so this would then be Fa1 minus Fa2, subtract mu k. If I sub Fn1 is m1g, this would then turn into mu k m1g is equal to m1 times a. Let's box this equation. And call it equation 2. That's as far as we can go for the first part. We need to figure out the system acceleration and tension. I have only one equation here with two unknowns. I don't know Fa2, and I also don't know the acceleration. So now we need to go to mass 2. So FBD for mass 2. Force of gravity straight down. Call it Fg2. Normal force points up. Once again, it's equal and opposite in magnitude. Fn2. We have an applied force that would be towards the right. Now here is where Newton's third law of motion would be applied. So if I was M2, I would feel the tug of this rope pulling me forward. We'll call that FA2. Now, I just want to, before I write the force of friction down, so this force, Fa2, and this force, Fa2, those are our equal and opposite forces in accordance with Newton's third law of motion. So that's the one implementation of Newton's third law of motion into this problem. It turns out for all of our other system problems where we were dealing with tension and connecting wire, we were applying Newton's third law of motion. We just didn't really realize it at that point. Okay, let's go back now and draw the force of friction. And we'll call that F2. Equations of motion start in the vertical direction. So this would be, assume up is positive. Find the sum of the forces in the vertical direction. No acceleration, equal to 0. Once again, it's balanced forces. Fn2 points up. Fg2 points down, negative. We'd have Fn2. Fg is m times g, so you'd have m2 times g. You need to be specific about the masses. Equals 0. And then this would give me Fn2. Add m2g to both sides is m2 times g. And we'll box that equation and call it equation number 3. To the x direction, assume right is positive. Find the sum of the forces in the x direction, which is equal to mass times acceleration in the x. Expand the equation of motion. Fa2 points towards the right, therefore it's positive. Ff2 points towards the left, it's negative. This is equal to, be specific about the mass now, so that's m2 times positive a. And then let's start to expand this a bit more. So Fa2 minus kinetic friction is mu k times Fn2. And this is equal to m2 times a. And we'll do the same substitution as we did before. So what I'm going to do is I'm going to take the equation 3, the Fn2, and I'm going to plug it in for Fn2 at the bottom. So then that would turn into Fa2 minus mu k m2g is equal to m2 times a. Box that equation, and we're going to call it equation number 4. Now, I want to write the system acceleration, let's go back for a second, in terms of the variables fa1, mu k, m1, m2, and g. The only variable we're not allowed to write the acceleration in terms of is fa2. So we need to solve the system, and the way we're going to solve the system is get rid of the variable that we're not allowed to write the acceleration in terms of. So we'll use elimination, and we can eliminate fa2 if we just add both of those equations together. And that's what I'm going to do on the next slide. Okay, so let's go. Add 2 and 4 to eliminate the variable fa2. Let's write these equations down. So equation 2, I believe, was fa1 minus fa2 minus mu k m1g is equal to m1a. And equation 4 was fa2 minus mu k m2g equals m2a. And we're just going to take these two equations and add them together. Because we're adding them, we don't have to worry about the distributive property. Okay, so fa1 just goes down. fa1. Negative fa2 plus fa2 would eliminate fa2. So that gets rid of it, so plus 0. You need to have negative mu k m1g plus negative mu k m2g. That deals with the left-hand side, and that would be equal to m1a plus m2a. All right, let's just do the work up here. I'm going to simplify both sides of the equation by factoring. So on the right-hand side, I would have fa1 minus, in the terms mu k m1g and mu k m2g, I have two common variables, that's mu k and g. So if I factor that out, mu kg, I would then have m1 plus m2. And on the right-hand side of the equation, if you factor out the common a, you'd have m1 plus m2. To get the a by itself, just divide both sides of the equation by m1 plus m2. So this would then turn into fa1 minus mu k g m1 plus m2 divided by m1 plus m2. We'll box that. And that is our answer to part A. Lots of work to get there, but now that we've done all that work, it's a lot easier to solve for other things in the system. Okay, so part B just wants me to just plug numbers in and calculate now. So let's plug it in. fa1 is 100 newtons minus mu k, which is 0.200, times the magnitude of the acceleration due to gravity, 9.81 meters per second squared, multiplied by the sum of those masses. M1 has a mass of, let's go back and double check here. Oops. M1 is 20 and M2 is 10. Okay. So 20 plus 10. 20 kilograms plus 10 kilograms. Divide this all by M1 plus M2. I put both the denominator and the numerator in its own set of brackets, and then calculate. By the way, up in the acceleration equation, you can't cancel out M1 plus M2 because it's not a common term in FA1. So you have to leave it in this format. We're going to two significant digits, and at two significant digits, I get an acceleration value that is 1.4 meters per second squared. So that's my answer to part B. Well, one of the answers to part B. I also want to figure out the magnitude of the tension in the connecting wire. Now, this is the nice thing about a system. Like, once you get the one variable, super easy to solve for the other one. The way we can solve for FA2 is we can either use equation 2 or we can use equation 4. So equation 2, we'd have to solve for FA2, or equation 4, solve for FA2. If you solve for FA2 in both equations, you should get the same number. And again, if you don't get the same number, it just means that you calculated A incorrectly or you derived the equation wrong. I'm going to choose the equation that has less terms in it because it's easier to calculate. So that's equation 4. So we'll use equation 4 to get the applied force in that connecting rope. So let's go back to my purple color. Okay, so that equation, 4, is FA2 minus mu k M2G is equal to M2A. Get FA2 by itself by adding mu k M2G to both sides. So that would then become M2A plus mu k M2G. When I plug numbers in, I want to plug in as little as possible, so I'm going to simplify one step further. I can factor out a common M2. That would now be A plus mu k times G. Then you'd have FA2 would be equal to M2 is that smaller mass, so 10 kilograms, times A, which is 1.4 meters per second squared. Let's put some brackets here. Plus 0.200 times 9.81 meters per second squared. Close the bracket off. And then we get FA2 is equal to, I got an answer of 33 newtons. You'll notice in like all my problems for the most part, I don't sub numbers into the last step of a problem. If you do happen to do university physics, you're going to find that a lot of problems don't actually give numbers. They'll be similar to example A or part A I have here, where it says like write the acceleration in terms of these variables, but doesn't give you any numbers to actually play with. I suppose that there's a couple reasons why this is done. One, it's testing your algebraic skills if like you can keep variables until the very end of the problem. The other thing is, now that you get an equation for acceleration, where's that equation for acceleration? Up at the top here. Well, now you could plug in any combination of numbers to calculate the acceleration. So you have an equation, a mathematical equation that models a scenario, and it could be solved for different values. So it'd be really easy to repeat the calculation if I just told you to plug in different numbers. So again, it's bad practice to sub numbers in right away. Usually you want to keep the numbers until the end of the problem. Okay. C says, using the equation derived in A, I want to identify which specific forces make up the net force on the system. Okay, so let's look at the one variation of Newton's second law of motion that tells me if I manipulate for A, Newton's second law would be sigma F divided by m. And what I want to do is I want to draw a comparison between this and the equation I derived in A. So let's look how things compare. Oh, we should clarify this is for the system. So wait, let's do this first. We'll say A for the system, just the magnitude, is sigma F divided by m. Okay, now let's draw the comparison. Okay, so A for the system would just be this A. The system mass, so we got the net force for the system mass, the mass of the system is just m1 plus m2. We're assuming all the other objects in the system, like that connecting rope, has negligible mass. And then what we're left to do now is to just compare the numerator of the equation. So I want to compare sigma F for the system to everything in the numerator of the equation I derived in A. And then I want to identify what forces make up the net force. So let's do that now, and I'll go back to purple color. Okay, so I know that the net force of the system is equal to what's in the numerator here in green. So that'd be FA1 minus mu K G M1 plus M2. Okay, we need to figure out this mass mu kg m1 plus m2 represents in terms of a force. So let's start expanding that. We're going to kind of undo what we did in when deriving the equations of motion. So we have FA1 minus mu k m1g minus mu k m2g. FA1 minus mu k m1g, according to equation 1, was just Fn1. Subtract mu k. M2g, according to equation, equation 1 told me that Fn1 is m1g. Equation 3 tells me that Fn2 is m2g. And what's the coefficient of friction times the normal force? Well, the force of friction. So the net force on the system as a whole would be FA1 subtract the force of friction on 1, subtract the force of friction on 2. So the reason the system is accelerating is because this applied force is larger in magnitude than the two opposing friction forces acting on M1 and M2. Okay, so that's it for the dynamics unit of study. There's some questions you can complete, if you like, in the Newton's third law of motion assignment. And I will talk to you in the next unit of study where we start to get into circular motion.